Hello, my name is Faith Jean, and I will be introducing Physics 2212 Lab 5 Magnetic Braking with Faraday. The purpose of this lab was to collect observational data of a magnet falling through a tube of aluminum foil, model the magnet falling through the aluminum foil computationally through GlowScript, and compare the observational and computed models. The preliminary findings show that the average time for the magnet to fall was 0.724 seconds. With a magnetic dipole of 1.4875 amps squared, the predicted time for the model was 0.435 seconds. And with the magnetic dipole of 2.166 amps squared, the predicted time matches the observed time of 0.724 seconds. Key concepts in this lab includes Faraday's law, which is a basic law of electromagnetism that predicts how a magnetic field will interact with an electric circuit to produce an electromotive force, and the electric field produced by the change in magnetic flux follows the loop and is in the same direction as the current. Other key concepts include magnetic force, which is the effect exerted upon either charge by a magnetic field created by the other, which is illustrated by IL cross B, and the magnetic force of the loop is IL cross B, where L is 2 pi r, and Ohm's law, which demonstrates the relationship between voltage, current, and resistance in an electrical circuit. The procedure for this lab includes marking the north pole of the magnet, measuring the mass of the magnet, measuring the length of the foil tube, the inner radius of the foil tube, and the width of the foil tube. Then dropping the magnet through the aluminum foil 5 times, measuring the time it takes for the magnet to fall from the moment it enters to the moment it exits. Then, using GlowScript, computationally modeling the same interaction and comparing the results. Here are the observational results for dropping the magnet through the aluminum foil 5 times. On average, the magnet fell at a time of 0.724 seconds. The length of the tube was 0.46, the width was 0.003, the inner radius was 0.0135, the total radius was 0.0165, the magnetic dipole was 1.4875 amps squared, and the mass of the magnet was 0.024 kilograms. This slide shows the GlowScript initial conditions for creating the loop. So we have mu naught over 4 pi constant, the resistivity constant, and the gravity constant. And then step 1 included the geometry of the tube and the properties of the magnet. This slide shows the code to derive the magnetic field of the bar magnet and the flux through each ring of the falling magnet. The illustrated equations are also on the right side. And this slide shows the while loop that was used to actually create the simulation, where the magnet falls through the aluminum foil tube and calculates the time it takes to fall. And this slide shows the results. So on the right side, when the magnetic dipole is 2.166 amps squared, the time in the tube was 0.724, and on the left, when the magnetic dipole was 1.4875 amps squared, the time through the tube was 0.435. When the magnetic dipole moment was the value from lab 3, the time for the magnet to pass was 0.435 seconds. Yet when the magnetic dipole moment was 2.166 amps squared, the simulation predicted the time for the magnet to pass through to be 0.724 seconds, which matched the observed result. Results suggest that the magnetic dipole moment from lab 3 is not completely accurate, and possible sources of error for this could be the friction between the magnet and the tube, and measurement of timing was wrong. So what if the resistivity of the conductor were reduced to as close as possible to 0? How would the dynamics of the falling magnet change? So nearly zero resistivity means nearly zero resistance. A zero resistance leads to a large induced current, meaning a larger magnetic force. Therefore, the magnet would fall with a slower speed because the force on the magnet is similar to the gravitational force. So what if holes or slots were cut into the tube? How would this affect the ring currents in the model? So holes or cuts disrupt the rings within the aluminum foil, and disrupting the rings reduces the induced current. Therefore, the magnetic force by the loop decreases. So the magnet falls with greater speed because the magnitude of the force on the magnet is much less than the force of gravity. Thank you for your time.